Hello and welcome everybody to this new video. In this video we are basically going to discuss the instructions which we provided on how to modify the VAM outputs so that it can be used properly in the FEEP software. So we looked at this document yesterday in which we are showing the stress resultants. Basically they are 2D stress resultants n alpha and m alpha, and they are resolved along the basis vectors or which are along the material coordinate lines in the deformed configuration. So it is called as convected basis, and the director vector, which is the normal, which you call it. It may not be perpendicular, may or may not be perpendicular to the surface. So let us look at a visualization of this expression, because this was something which was not fully clear to most of us. So let us now look at a brief visualization of the same. So here let me draw the undeformed and deformed configurations first. So this is the undeformed configuration of the shell. So we can call it reference or undeformed. Oops. Reference or undeformed configuration, and this is going to a deformed configuration. Okay, and this is we are calling as with S, and this is your current configuration. Okay, and both of these undeformed and deformed configurations are connected through a Euclidean space. So let me draw the Euclidean space over here. So zeta 1, zeta 2 and zeta, and the same element if we draw in the Euclidean space, the lines will not be curved, it will be straight, like this, somewhat like this. So let us call this length as d zeta 2 and this height as d zeta. Okay, and the vector on this face, so this face is along this direction, and this vector is e1. Okay, and the area vector, if you talk about, that area vector will be dA vector. Okay, so this is our Euclidean space. Okay, I think there is I here. Okay. Now if we want to write this dA vector magnitude, so it will be d zeta 2 times d zeta, or dA vector, if you want to write, this will be nothing but the unit vector along the dA vector is e1, so e1 hat I can write, times d zeta 2 times d zeta. So this is the dA vector. Now we want to write the expression of dA vector in the current configuration in terms of this dA vector. So there is a standard formula from continuum mechanics, which is nothing but dAi is equal to J F inverse Si dAs. This is in indicial notation, and in the vector notation or matrix notation also you can write this is J F inverse transpose dAs. Now this is basically used over here to write the a general dA vector in the current configuration. So if we look at the paper here, in the part 1 of the series of papers by JC Sim et al, we have this expression in equation 4.2. This is the area vector or n hat ds written in the current configuration in terms of the dA vector of the Euclidean space. So it is the same relationship. So as we have seen that we have written this DAI is equal to J F inverse SI DAS. So what we can write this as DA vector components in matrix form is equal to basically that they are calling here as D zeta 1 on the left hand side. D, so I'll just try to write that symbol like this. Okay, so this is that symbol, and that is equal to J and grad phi, capital phi, grad phi inverse transpose dA vector, and this dA we can substitute as E1 E hat 1 d zeta 2 times d zeta, sorry, d zeta 2 times d zeta, right? I hope it is visible. Yeah, so this is what we have obtained, and this relationship is given over here in this equation 4.2. So this is nothing but J grad phi inverse transpose times dA. So this is d small a. Now this is the area vector in the current configuration, and now it is expressed in terms of G superscript 1, which is nothing but contravariant basis vector. Okay, which we can write in terms of the phi and t map which we have. So derivative of phi will give us G, and G subscript 1, G subscript 2 and G subscript 3, and from those we can obtain the contravariant components. So this we have, and now if we multiply this area vector with sigma, we will get the corresponding force which is acting on any general area in the current configuration. So let us come back to this screen. So we can see that Euclidean space can connect both the undeformed deformed geometries through phi and lambda, which is related to director. Okay, so this is how this is connected, and now if we bring in this area to a zoomed in version, okay, so now we can write this as this. So let us draw this figure again. Okay, now we have this d small a. Okay, this is this vector we have, and if we multiply this d small a vector with sigma, which is the Cauchy stress, which is expressed as force acting in the current configuration per unit area of the current configuration. So that sigma we multiply with dA, will get a force. So that force could be in any direction. Let's say this is the direction of force, and let us call it n1 vector. Similarly, on this face we will get n2 vector. So both of the faces will get n1 and n2. Now this n1 and n2, let's consider just n1 for now. If we can resolve this n1 along any basis directions as per our requirement. If we choose to resolve this n1 along the convected basis, that means along the coordinate lines. So for this shell element, we have the coordinate lines along this and along this. Okay, these are the coordinate lines which we are calling in the mid surface. It is represented as A1 or A2 or G1, G2, like that they are represented. Okay, so now if we resolve it along this direction, then what we get is the normal component will be N11. Okay, this is the component now, N11. Then similarly on this face we'll get N22, and the component of this force along this direction will be N21, and here it will be N12, and then there will be a component along the director vector direction, okay, which is along here T. So this will be Q1, and from here what we'll get will be Q2. So these are total 6 components. Okay, so we got N11, N21, Q1. These all from N1, N1 force, and N2 force will give us N22, N12, and Q2. Now this N21 and N12 may not be equal because this is not symmetric in general. So then there is next step which we'll talk about later. That is a phi procedure where we transform this to make it n tilde. These components are now right now without tilde. Later on we'll convert it into n tilde beta alpha. So then they will become symmetric. So these are the components of n1 and n2. Similarly, so this expression, I will show you the expression in the PDF. So right now this is, we have just written the expression in terms of the sigma. Now if we go down, this is the actually the expression of n alpha. So it is just sigma times that d small a vector, and it is normalized by dividing this with the Jacobian, average Jacobian at not average Jacobian, the mid surface Jacobian, okay, which is represented like this, a1 cross a2, and this is how we get n alpha. So both n1 and n2 are the forces. Basically they are the integrations of the sigma Cauchy stress over the thickness. So that's how we get this n alpha, and similarly m alpha is the moment of that force. So we take x minus phi, so we'll get the component of moment along the director vector, and that we take cross product with the shear stress force sigma times d small a. So we will get this m alpha, and in the same way we can resolve m alpha also along these components. So then we will get the components of m alpha also. So let us come back to that same instructions page. Here what we are saying is this n alpha and m alpha have to be resolved along the convected basis. Okay, so I hope this will be clear now that what are n alpha and what are its components. And in this process we have to also resolve t comma alpha. So t is the director vector. So in VAM case we'll have a normal vector, or you can say b3 vector. So its derivative, when it is resolved along the convected basis, we get the lambda values. These lambda values are then used along with this n beta alpha and m beta alpha values to get what is called as the symmetric stress resultants. Okay, so these are going to be used as inputs in the Phoebe software. So that was all, I think. If you want to look at the detailed expressions of n alpha and m alpha, they are given in the appendix of part 1 of the series of papers. So here we have the expression of force n alpha in terms of the 3D Cauchy stress also. Okay, so this also we can obtain, and then the expressions of those components in terms of 3D stress, that also can be written. So all these things we have over here. So I hope this video was helpful, and if any further questions are there, please do let me know, and I'll try to resolve those as well. Thank you very much. So I'll be sharing the PDF of this drawing, what I have shown in this description, and you can refer to that also if it is needed. Thank you very much.